Hi everyone. I'm going to continue here with the expansion work example. So this is example 2. And again, this is a situation where, if you think about it, it's really a type of situation where there's expansion work involved. In this case, we have a staple gun. And these staple guns, usually they have compressed gas in it. And the compressed gas is, in this case, at 1.5 atmosphere and 150 milliliters. When you press the trigger, what you're allowing the gas to do is you're allowing the gas to expand against atmospheric pressure, which is at 1. So they eventually will equilibrate. The 1.5 will eventually become 1. And that's going to happen at constant temperature. So when you let that expand, of course, the staple is pushed out because of the expansion. Now, the question is, if the heat generated during this process is 5.5 joules, what's the amount of work done by the staple gun? And here you have that conversion factor again, which is 1 liter atmosphere is equal to 101.3 joules. Remember that we had that earlier as well, but in that case we were using the 2 units of the gas constant, but if you were to calculate it, you'd get this number. Okay, so if you look at this example, it's really a work expansion. It's asking you for work. Now we know that for work, we want to calculate work, we're going to need to do our P external calculation times delta V. And again, delta V is final minus initial. In this case, the final volume is the volume when the gas stops expanding, and the initial volume is the volume at the beginning, right? So then, so this is really negative P external times final volume minus initial volume. Okay. Now, we know that the initial volume we know is 150 milliliters. We don't know what the final volume is, but one of the keywords that is given, if you read through this question back again, it says that it's an ideal gas and it's expanding against atmospheric pressure at constant temperature. Okay, now the gases of course don't leak out of this, right? It just expands, and then when you pull, you get the trigger set up again, that it goes back to the same position again, 1.5 and 150 and so on. So in other words, the gases still remain there. It's just that the pressure is changing from 1.5 to 1, and as a result the volume is going to change as well. Now, so if you remember in the previous topic when we talk about gases, we talk about that relationship, which is P1 V1 O equals to P2 V2, and this is of course what we refer to as Boyle's law. Okay, so Boyle's law is that if you were to pressure and volume are inversely related to each other. So now what we know is that we're starting with some initial pressure and volume. We know the final pressure has to be 1 because that's what it's expanding against, and we have to calculate final volume. So we can then just solve for V2 in this case, which is P1 V1 over P2. And if I were to plug in my numbers, what I'm going to put in is 1.5 atmosphere, and then my initial volume is 150 milliliter, and then my final pressure is 1. So if I were to do this calculation, my final volume should be 0.225 liter. And having this number now allow me to calculate my work. My work is just negative P external, which is 1 atmosphere. Final volume in this case is 0.225, and initial volume is 0.15 liter. And so when you calculate this, you get negative 0.075. I'm sorry, not 0.00, but 0.075 liter atmosphere. Now you notice that the negative stays because this number here is positive. So when you multiply that with the negative 1 atmosphere, you get negative 0.075. I want to emphasize again that the negative really does, it's not negative in this regular sense of the negative meaning in math. Negative here has a thermodynamic meaning, which means that energy is going out of the system. Okay, so you always have to kind of keep that in mind. Now this could be converted to joules, right? We're using our conversion factor from liter atmosphere to joule. In this problem, you're actually given that conversion factor directly, but you can derive it, remember, from the gas constant. So this is 101.3 to 1. And if you do that calculation, you should get negative 7.6 joules. Now, if you read the question back again, it also tells you that there's heat generated in the process, which is 5.5 joules. But that's one of the thing to point out here, that in this particular case, the heat actually is irrelevant to solving the problem, because what you're being asked is work. So one of the things you want to be able to do over time when solving problems in the sciences is you want to be able to determine what information is useful to solve the problem and what information is not useful to solve the problem, because a lot of times you'll get a lot of information, but only some of the information will be useful, and most of the other information is probably just not really relevant for solving your problem. So one of the skills that you should develop over time is the ability to tell the difference between what's important and what's not important, what's relevant and what's not relevant.